we're back. Now we're going to do collision problems. So we have this 5 kilogram mass going to the right at 3 meters per second, 8 kilogram mass going to the left at 4 meters per second. This is when conservation of momentum really comes in handy. Because in reality, these two things exert absolutely no normal force on each other. They touch, the normal force increases, and then it drops off as they start to separate. If they separate. So the normal force goes from 0 to something bigger than 0 magnitude-wise, and so therefore the force is not constant. Now, if we tried to take this from the point of view of F equals ma, it'd be very difficult to do because the force isn't constant, and in physics 151 we don't really have the methods for dealing with that. In 251 we have calculus, and so we have slightly more tools in order to deal with it, but it's still incredibly difficult. We'd have to somehow model how the force changes, and it's probably the force, it's somewhat of a triangle from the experimentation I've done. And so we are now dealing with, we don't care what happens during the interaction. What we do know is that the momentum beforehand equals the momentum afterwards. And so first thing we need to know is what is the total momentum beforehand? This is the capital P in a couple of videos ago. So the initial momentum is equal to the momentum of the 5 kilogram mass, and I'm just going to put a little subscript 5 here to indicate the 5 kilogram mass. You could also put a 1 because it's the first one, or a 2, just as long as the subscripts are different. But I tend to put my subscript equal to the mass, hoping the masses aren't the same, plus momentum of the 8, which is mass of the 5 times the velocity of the 5 initially, plus mass of the 8 times the velocity of the 8 initially. So all I'm doing is just finding the momentums of each. We've already done this on a previous video. So this is 5 times 3 plus 8 times -4. And again, the previous video talks about the fact that it is going in the negative direction. I'd already predefined to the right as positive. If I said to the left was positive, then these signs of my velocities here would change. And just for those who did not quite catch it, that's the mass, that's the velocity, that's the mass, that's the velocity. So we end up with here is 15 minus 32, which is -17 Descartes. So that is the total momentum before the collision. However, now if I ask you what is the total momentum after the collision, well, that's the total after the collision. That's the power of conservation of momentum. Once I figure out what the initial value is, I know what the total final value is. However, what we don't know is the individual. And so in order to figure out what's going to happen after the collision, we need to know what type of collision it is. And there's a couple of basic types. So hopefully you've paused this in order to write this stuff down for those who are writing it down. If you're just looking at it and let it sort of go over you in a wave, I recommend looking at it a number of times just so you get it down. So what I want is I need to describe what types of collisions there are. So I do need to erase this. I am going to write over here just so that I can refer to it later. So the momentum initial is equal to the total momentum final, which is equal to -17 Descartes. And again, as mentioned in the last video, I need to define it, and it's still written up in the upper left-hand corner. So now let's erase. So the different types of collisions depend upon what happens to the kinetic energy. If you recall, and you should know this, matter of fact, let's just pretend it's going to work beautifully. Everyone's watching at the same time. When I ask what's the formula for kinetic energy, I'm about to ask it, you should know what it is. So what's the formula for kinetic energy? I'm hoping you said the correct answer because that is the one formula I do expect you to have memorized absolutely. So K is equal to 1/2 mv squared. Again, no vectors involved here, it is just scalars. So the question is, do we gain, lose, keep the same amount of kinetic energy? What's going on here? So changing kinetic energy. So let's start if they stick together. there will be kinetic energy loss, and we can actually show that mathematically. But if they stick together, there is kinetic energy loss. This is the change in kinetic energy is less than 0. That indicates that there's a loss. And the type of collision, I'm going to write this slightly above there. So type of collision. All right, there are 2 naming conventions. As a matter of fact, I'm going to introduce a 3rd one just to eliminate, I think it eliminates confusion, but whether it does or not, I'm doing it anyway. So there's naming convention 1, where this is known as perfectly inelastic. A perfectly inelastic collision is they are going to stick together. Naming convention 2 this is called inelastic. So in this naming convention 2, if it bounces, there's something elastic is going on there, even if it doesn't bounce up to the same height. There's also bounce off each other, bounce. And the change in kinetic energy is still lost. We lose kinetic energy. In the first convention, this is known as inelastic. In the second convention, this is known as elastic. And I hope at this point you can see why there's potential confusion. Now, generally authors will pick one or the other, but the trouble is if you're looking at different sources, how do you know which one it is? And frankly, different textbooks that I'm using do it differently, and so in order to, because I have issues trying to remember which book does which convention, that's why I come up with the Fox method over here, and we'll deal with that later. There's also the bounce, where the kinetic energy stays the same. So there is no change in kinetic energy. Kinetic energy is conserved. Not overall, there's not a conservation of kinetic energy rule in physics. There are just some situations where kinetic energy is conserved, especially in high energy physics where things like friction don't really make any sense when you're dealing on a particle level. And so this is the type of thing that I dealt with in terms of my doctorate. Under this convention here, it's called elastic. And under this convention, it is perfectly elastic. And then if we have a gain in kinetic energy, so bounce, no explosion, and I'll put explosion in quotation marks just as a generic term for something forcing things apart, and kinetic energy is gained. They at least agree on this one. They call this impossible. All right, so my naming convention here. If they stick together, because the words elastic and inelastic have become sort of tricky here, we need to, I go for the ones that are not ambiguous. I go for perfectly inelastic. So the Fox naming is I use perfectly inelastic. For the ones where they bounce and kinetic energy is conserved, I call that perfectly elastic. And for the one in the middle, I struggled with what to call that one. A student suggested a couple years ago, imperfect, and I like that, so I call this imperfect. And the one which they say is impossible, having been a child of movies growing up, I call this flubberesque. And if you're not familiar with that, there is the Robin Williams movie called Flubber, as well as I highly recommend the original, The Absent-Minded Professor with Fred McMurray, as well as there was a Harry Anderson version of Absent-Minded Professor. Excellent films, family friendly and not frenetic like the Robin Williams ones. And you know, the special effects, come on, it was the 50s. So anyway, flubberesque. And that's it. So what we're going to do in the next couple of videos is we're going to go through this collision here, and we're going to take a look at it from these 3 points of view here. I will say mathematically, the imperfect collision is probably the hardest mathematically because you basically have one technique to solve it. The perfectly elastic, there are 3 techniques to solve it, and I will go through all 3 techniques. That'll probably be 3 separate videos. And the Fulleresque one is just something where I'm making up numbers and we just see what happens. And sometimes we gain, sometimes we lose. It's the type of thing where I give a collision, I tell you one piece of information for after the collision, you figure out the missing piece of information, and then I ask what kind of collision is it. That's the type of situation where Fulleresque comes into play. One other thing, the explosion, when I talked about no explosions here, if I have a shell being set up and suddenly it explodes into 2 pieces, or 3 pieces, depends on how complicated I want to make it, explodes into 2 pieces, it's a 2-dimensional problem. But recognize that is a gain in kinetic energy. However, it is just the reverse of this, where they stick together. In the classic collision problem, they start out apart and they stick together. In that problem, they start out together and they end up apart. I don't give that a separate category. It's just the reverse of the perfectly inelastic collision. And so I'm going to stop it here, and I will see you shortly in the next one.